Look up at the night sky, and you'll see countless stars, swirling nebulae, and spiral galaxies, each one a masterpiece of cosmic design. But hidden among these celestial wonders are the true oddballs of the universe, ring galaxies. Picture a shimmering, perfectly symmetrical hoop of stars floating in the void, as if some cosmic hand delicately sculpted it into existence. These bizarre structures aren't just beautiful, they're cosmic mysteries that defy everything we thought we knew about how galaxies form and evolve. What if I told you these strange rings hold secrets that could rewrite the rules of astrophysics? Imagine a galaxy so peculiar that astronomers first thought it was a glitch in their telescopes. A place where stars don't spin in elegant spirals but instead race around in a colossal, fiery loop. How does something like this even happen? The answer is as violent as it is awe-inspiring. These rings are the aftermath of cosmic collisions. Galactic smash up so powerful they send shockwaves through space, ripping apart entire star systems and reshaping them into these otherworldly hoops. But that's just the beginning of the story. Within these enigmatic rings, we've discovered phenomena so strange, so inexplicable, that they challenge our very understanding of physics. Black holes behaving in ways they shouldn't, ghostly dark matter bending light into impossible shapes, and stars forming at speeds that seem to break all the rules. Today, we're diving deep into 30 of the most mind-bending mysteries hidden within these ring galaxies. From the haunting beauty of Hoag's object to the chaotic dance of the Cartwheel Galaxy, each one holds clues to the universe's greatest puzzles. Why do some of these rings glow with bizarre, unexplained light? How can entire galaxies reorganize themselves into perfect circles after catastrophic collisions? And what do these cosmic anomalies tell us about the fate of our own Milky Way? Buckle up, because by the time we're done, you'll never look at the night sky the same way again. The universe is stranger, wilder, and more mysterious than we ever imagined, and ring galaxies are the key to unlocking its deepest secrets. One of the most puzzling features of ring galaxies isn't what they contain, but what they don't. At the heart of most galaxies, you'd expect to find a dense, bright core packed with stars, gas, and often a supermassive black hole. Yet some ring galaxies stare back at us with a haunting emptiness, their centers eerily dark. How does a galaxy lose its core? It's like finding a donut with no hole, a cosmic contradiction that shouldn't exist. The leading theory points to a cataclysmic event, a head-on collision between two galaxies. Picture a smaller galaxy plunging straight through the heart of a larger one like a bullet. The gravitational shockwave from this impact could scatter the core's stars outward, leaving behind a ghostly ring where the center once thrived. But here's the twist: simulations show this process should still leave some trace of the original core. Yet in galaxies like Hoag's object, the void is nearly perfect. Astronomers are left scratching their heads, wondering if something even stranger is at play. Could a supermassive black hole be the culprit? Some suggest these invisible giants might devour the surrounding stars or fling them away with their immense gravity, effectively erasing the core from view. Others speculate that dark matter, the universe's most elusive substance, might be warping space in ways we don't yet understand, hiding the core in plain sight. Then there's the wild card. What if these galaxies never had cores to begin with? A handful of scientists argue that under rare conditions, gas might collapse directly into a ring, bypassing the usual central cluster entirely. The mystery deepens when we compare these coreless rings to their more traditional cousins. Galaxies like the Cartwheel still show remnants of their original centers, proving that not all collisions wipe the slate clean. So why do some disappear without a trace? Every unanswered question pushes astronomers to rethink the rules of galactic evolution. These ghostly cores aren't just celestial oddities, they're cosmic crime scenes, and the evidence we're gathering could rewrite our understanding of how galaxies live, die, and transform in this violent, ever-changing universe. Now let's turn to one of the most breathtaking sights in the cosmos: ring galaxies that blaze with newborn stars, defying the typical scattered star formation we see in most galaxies. Normally, stars are born in messy, uneven pockets of gas and dust, scattered across spiral arms or clustered in irregular knots. But in these cosmic rings, star formation happens with almost mathematical precision, igniting in a brilliant, fiery circle that looks more like a celestial firework than a galaxy. What causes this extraordinary burst of star birth? The answer lies in the same violent collisions that shape these galaxies in the first place. When two galaxies collide, particularly when a smaller one punches straight through the center of a larger one, the impact sends shockwaves rippling outward like ripples in a pond. These shockwaves slam into the surrounding gas, compressing it with unimaginable force. And just like squeezing a balloon until it pops, that sudden pressure triggers a frenzy of star formation. Within these shockwave-driven rings, gas clouds collapse at an astonishing rate, igniting thousands, sometimes millions, of young stars in a single luminous band. But here's the real mind-bender. Unlike typical galaxies where star formation is sporadic and chaotic, these rings create stars in nearly perfect synchronization. The Cartwheel Galaxy is one of the most dramatic examples. Its outer ring ablaze with blue-white supergiants, stars so young and hot they outshine entire clusters found in common galaxies. And because the shockwave travels in a near-perfect circle, the stellar nurseries form in an eerily precise loop, as if the galaxy itself is following some cosmic blueprint. Yet even as we marvel at this spectacle, mysteries linger. Why do some rings produce stars at rates hundreds of times faster than normal galaxies? Why do these star-forming regions stay so sharply defined rather than spreading out over time? Some astronomers suspect that dark matter may play a role, its invisible gravitational grip keeping the ring's structure intact. Others wonder if magnetic fields, twisted and amplified by the collision, act like cosmic fences, corralling gas into these perfect circles. And then there's the ultimate question: what happens to all these stars? Normally, such intense star birth would quickly exhaust a galaxy's gas reserves. But some ring galaxies seem to defy even that rule, continuing to produce new stars for billions of years. Are they somehow replenishing their gas supply, or is there another force at work, stretching the laws of physics beyond what we currently understand? Every flicker of light from these star-forming rings holds a clue, and with each discovery, we're not just learning about galaxies, we're uncovering the hidden rules that govern the life and death of stars themselves. If there's one thing that haunts astronomers more than the voids at the hearts of ring galaxies, it's the invisible enigma lurking within their halos: dark matter. This mysterious substance, which makes up most of the universe's mass, is already baffling enough, but in ring galaxies, it defies expectations in ways that upend our cosmic playbook. Normally, dark matter wraps around galaxies in a roughly even spherical halo, like an invisible cocoon. But in these cosmic rings, its distribution is chaotic, patchy, and sometimes even missing where it should be most dense. How do we even know this? The answer lies in one of the universe's most elegant tricks: gravitational lensing. When light from distant galaxies passes through a ring galaxy's dark matter halo, it bends like a straw appearing to bend in a glass of water. By mapping these distortions, astronomers can reconstruct the hidden mass, but what they've found is anything but ordinary. In galaxies like the Cartwheel, dark matter isn't smoothly distributed. It's clumped, warped, or even stretched into strange, asymmetrical shapes. Some regions show gravitational pulls far stronger than expected, while others are eerily weak, as if dark matter has been scooped out like cosmic ice cream. Compare this to spiral galaxies like our Milky Way, where dark matter behaves predictably, its density tapering gently from the core outward. So why the chaos in ring galaxies? The collision that forms these rings might hold the key. When galaxies smash together, their dark matter halos, normally stable and diffuse, could get tangled, shredded, or even flung outward by the sheer force of impact. Some simulations suggest dark matter particles might interact with each other during these crashes in ways we don't yet understand, clumping unpredictably. Others propose that the violent reshaping of the galaxy's gas and stars could drag dark matter along with it, leaving gaps or pileups in its wake. Then there's the most tantalizing possibility. What if dark matter isn't just passive scaffolding, but something more dynamic? A handful of rogue theories suggest certain types of dark matter might respond to gravity differently in extreme environments like the high-energy chaos of a galactic collision. If true, ring galaxies could be our best laboratories for uncovering dark matter's true nature. Every distorted image, every unexplained gravitational tug, is a clue waiting to be deciphered. And as we peel back these layers, we're not just solving a galactic mystery, we're rewriting the rules of the cosmos itself. Among the strangest sights in our universe are galaxies that wear their rings like celestial crowns, polar rings where a luminous band of stars and gas spins at a right angle to the main disk, defying all expectations of galactic architecture. Picture a spinning plate balanced atop a pole, and you've got the basic idea, except this cosmic balancing act spans tens of thousands of light years. Hoag's object is the poster child for this phenomenon. Its nearly perfect ring glowing blue with young stars, encircling a golden core like a halo frozen in space. But don't let its beauty fool you. This delicate arrangement is a ticking time bomb, a fleeting moment in a galaxy's life that few survive intact. These polar rings are cosmic accidents, born from some of the rarest and most violent mergers imaginable. Unlike the head-on collisions that create classic ring galaxies, polar rings require a precise, sideways encounter, like a smaller galaxy sideswiping a larger one at just the right angle. The gravitational dance that follows is chaos incarnate. The victim galaxy's disk gets stretched and twisted, while the intruder's gas and stars are ripped away, forming a new ring that orbits perpendicular to the original plane. It's the astrophysical equivalent of throwing a dart blindfolded and hitting the bullseye twice. What makes these structures so extraordinary is their fragility. Gravity abhors instability, and a misaligned ring is like a spinning top wobbling toward collapse. Over time, tidal forces and internal friction should tear these rings apart, scattering their stars back into the galactic disk or flinging them into the void. Yet against all odds, a handful survive for billions of years. Hoag's object, for instance, shows no signs of disruption, its ring pristine, as if suspended in time. That longevity poses a riddle. Some theorists argue that dark matter might act as an invisible scaffold, its gravitational pull stabilizing the ring. Others suggest magnetic fields woven through the gas like cosmic thread could hold the structure together, but the most intriguing possibility, these rings might be younger than they appear, constantly replenished by streams of intergalactic gas or repeated encounters with smaller galaxies. Each hypothesis leads to more questions than answers, forcing astronomers to reconsider how galaxies interact and how long the scars of those encounters can last. And then there's the ultimate irony. These unstable rings might hold the key to understanding galactic evolution. Their tilted orbits let us map a galaxy's hidden dark matter in 3D, while their star-forming gas reveals how galaxies recycle material over eons. Every wobble, every kink in these cosmic hoops is a clue, a whisper from the universe about the forces that shape everything we see. Polar rings shouldn't exist. And yet, there they are, spinning defiantly against the darkness, reminding us that the cosmos loves to break its own rules. Some of the most haunting signals from ring galaxies don't come from starlight at all. They're ghostly whispers crackling across the radio spectrum, long after the events that created them should have faded into silence. Unlike the predictable pulses of pulsars or the brilliant beacons of quasars, These emissions are unpredictable, uneven, and often tied to regions that look utterly ordinary in visible light. It's as if the galaxies themselves are broadcasting secrets in a language we're only beginning to decode. Take the case of one peculiar ring galaxy studied by radio telescopes deep in the Australian outback. Its outer ring glows faintly in optical light, but when viewed through radio eyes, it erupts in sprawling, filamentary structures, vast ribbons of energy stretching far beyond the galaxy's visible edges. These aren't the tightly wound jets of an active supermassive black hole, nor the rhythmic bursts of spinning neutron stars. Instead, they resemble the aftermath of an explosion, like echoes of a catastrophe that occurred billions of years ago. The strangest part, there's no obvious source, no quasar, no visible black hole devouring matter, just this eerie, lingering radio glow. Astronomers have a working theory, and it's as dramatic as it is unsettling. Supermassive black holes, those invisible giants lurking in galactic cores, might be the culprits, but not in their usual active state. Imagine a black hole feasting voraciously in the distant past, gorging on gas and stars during the galaxy's violent formation. As it fed, it would have launched jets of charged particles at near light speed, carving bubbles of radio-emitting plasma into intergalactic space. Then, abruptly, the banquet ended. The black hole ran out of fuel, fell silent, and faded into obscurity. But those radio bubbles, they're still there, expanding slowly, their faint signals a fossilized record of ancient fury. Yet even this explanation raises new questions. Why do some ring galaxies show these emissions while others, with similar collision histories, remain radio quiet? Some researchers speculate that magnetic fields, woven through the galaxy's gas like invisible spiderwebs, could trap and amplify these signals for eons. Others wonder if dark matter plays a role, its gravitational influence somehow preserving these structures far longer than physics predicts. And then there's the unsettling possibility that what we're seeing isn't just ancient history, that somewhere in these rings, black holes might be flickering back to life in ways we've never seen. Every faint radio whisper forces us to reconsider how black holes live, die, and leave their mark on the cosmos. These signals might be faint, but their implications are thunderous, hinting at a universe where even the quietest corners have stories of violence to tell, if only we know how to listen. Galaxies aren't just isolated islands in space, they're predators. And among the most ruthless are ring galaxies, which don't just form from collisions but sometimes consume their neighbors whole, leaving behind twisted stellar trails like cosmic breadcrumbs. Picture a vast, luminous ring drifting through the void, its gravity reaching out like invisible fingers to snatch stars from a passing dwarf galaxy. Over millions of years, the victim is torn apart, its stars smeared into long, shimmering streams that orbit the ring like strands of stolen jewelry. This process, called galactic cannibalism, isn't just violent, it's slow, methodical, and eerily beautiful. As the smaller galaxy nears the ring, tidal forces stretch it like taffy, pulling stars loose in a process resembling the way Earth's gravity tugs on oceans to create tides. But on a galactic scale, the effect is far more dramatic. The stolen stars don't just form a neat ribbon. They're flung into chaotic orbits, some spiraling into the ring, others looping far beyond it in vast, looping arcs. Over time, these trails fade, their stars assimilated into the larger structure, subtly altering the ring's shape and chemistry. What makes ring galaxies especially voracious is their unique geometry. Unlike spirals with their tightly wound arms, a ring's open structure creates a gravitational hook that can capture passing galaxies more easily. Take AM0644, a ring galaxy caught in the act of devouring a smaller companion. Astronomers have traced faint stellar streams arcing away from its outer edge, the ghostly remains of a meal half consumed. And just like fingerprints, these streams tell a story. By studying their curvature and star density, scientists can reconstruct the victim's original size, its trajectory, even how long ago the feast began. But here's the twist: this cannibalism isn't just destructive, it's transformative. The ingested stars bring fresh gas and heavy elements, reigniting star formation in the ring. Younger, bluer stars appear along the cannibal galaxy's path, as if the ring is stitching its new acquisition into the fabric of itself. Yet some rings, like NGC 2915, show bizarre, lopsided star trails that refuse to blend in, hinting at mergers so recent the galaxy hasn't had time to digest its prey. The real mystery: why some rings become serial cannibals while others ignore passing galaxies entirely. Dark matter may hold the answer. Simulations suggest that rings with lumpy, asymmetric dark matter halos are far more likely to capture and shred smaller galaxies, while evenly distributed halos let them pass unscathed. It's a cosmic balancing act, one that could determine whether a ring galaxy grows ever larger or remains a solitary wanderer in the dark. And then there's the ultimate irony: this cannibalism might be seeding the ring's destruction. Every merger adds chaos, destabilizing the ring's perfect shape over billions of years. One day, these graceful hoops may unravel entirely, their stolen stars scattering into the void, proof that even the fiercest predators in the cosmos aren't immortal. At first glance, the vibrant colors of ring galaxies might seem like simple decoration, cosmic paint splashed across the void. But those hues tell a story of life, death, and galactic resurrection. Some rings blaze with an electric blue, their light dominated by massive, short-lived stars hotter than our sun's core. Others glow a deep, rusty red, their populations aging quietly like embers cooling after a fire. This stark divide isn't random, it's a cosmic clock, revealing exactly when and how these galaxies were reborn through catastrophe. Take the Cartwheel Galaxy, its outer ring shimmering blue like a sapphire dropped in space. That brilliance comes from stellar nurseries less than 10 million years old, infants by cosmic standards. When the collision that formed this ring occurred, shockwaves compressed vast clouds of hydrogen gas, igniting frantic star formation. Blue stars dominate because they're the brightest, outshining their smaller, redder siblings, but their glory is fleeting. Within a few 100 million years, these giants will explode as supernova, their death seeding the ring with heavy elements and leaving behind dimmer, longer-lived red stars. Now contrast that with older rings like Hoag's object, where the golden red glow hints at a quieter history. Here, the original burst of star formation faded billions of years ago. Without fresh gas to fuel new stars, the population aged uniformly, leaving behind cooler, redder stars that burned steadily for trillions of years. But the real mystery lies in the exceptions, rings that defy this timeline, like NGC 7020, where blue and red regions battle for dominance in the same structure. The key lies in the galaxy's gas reserves at the moment of collision. Gas-rich galaxies become blue rings because they have the raw materials to birth stars immediately after impact. Gas-poor galaxies, already starved before the collision, can only muster a few new stars before fading to red. But some rings, like AM0644, show patches of both, evidence of multiple collisions or late-arriving gas clouds reigniting star formation like matches struck in the dark. Yet even this explanation has cracks. Why do some gas-rich rings fade inexplicably fast, while others, like the Cartwheel, keep producing blue stars far longer than models predict? The answer might lie in dark matter's unseen grip, its gravity governing how efficiently gas is funneled into star-forming regions, or perhaps magnetic fields twisted by the collision act as cosmic dams, regulating the flow of gas over billions of years. And then there's the ultimate irony: the reddest rings might secretly be the youngest. In rare cases, a collision could trigger such rapid star birth that all the gas is exhausted almost immediately, leaving the galaxy to redden far sooner than expected. Like a firework that burns out in seconds, these rings might skip the blue phase entirely, their true age hidden beneath a veil of false maturity. Every color tells a story of violence, time, and the delicate balance between creation and decay. And as we unravel these chromatic clues, we're not just studying galaxies, we're learning how the universe itself chooses to paint its masterpieces, one cataclysm at a time. Not all ring galaxies spin in perfect, flat circles like cosmic wedding bands. Some twist and warp into shapes that defy logic, as if sculpted by invisible hands. These contorted rings bend into bizarre, asymmetrical forms, their once pristine symmetry distorted by forces we're only beginning to understand. Hubble has captured some of the most striking examples, like a spiral staircase flung into space or a celestial ribbon caught in a cosmic breeze. And the closer we look, the stranger these structures become. The leading suspect, unequal collisions, galactic smash-ups where one galaxy doesn't strike dead center, but instead delivers a glancing blow. Picture a pebble skimming across a pond. The ripples aren't neat circles but elongated ovals higher on one side. Now imagine that pebble is a dwarf galaxy and the pond is a massive spiral. The impact sends shockwaves unevenly through the disk, triggering star formation that's lopsided, leaving the ring warped like a vinyl record left in the sun. Galaxies like ESO 509-017 showcase this perfectly, their rings kinked at odd angles as if frozen mid-twist, but collisions aren't the only explanation. Some warped rings might be victims of cosmic sabotage, small, hidden galaxies lurking just out of frame, their gravity tugging on the ring like marionette strings. Hubble's deep field images reveal faint smudges near these twisted rings, potential culprits too dim to see clearly. These stealthy dwarfs could orbit just outside the main galaxy, their pull gradually distorting the ring over billions of years, bending starlight into surreal curves. Then there's the dark horse theory, dark matter again, but this time not as a stabilizing force. Simulations suggest that if dark matter clumps unevenly around a galaxy, its gravitational pull could torque the ring out of alignment, like an invisible hand pressing down on one side of a spinning top. The resulting warps wouldn't match predictions based on visible matter alone, a tantalizing clue that dark matter's distribution might be far lumpier than we thought. The real mystery lies in the exceptions, rings that warp in ways none of these theories fully explain. Take UGC 4599, its outer ring twisted into a near-perfect sine wave, as if vibrating to some inaudible cosmic frequency. No collision model reproduces this pattern, and no dwarf galaxy lurks nearby to account for the distortion. Could magnetic fields, stretched and twisted during the ring's formation, be pinching the gas into these strange shapes? Or is there some undiscovered instability in how rings evolve, a hidden law of galactic physics that only reveals itself in these rare, twisted survivors? Every warp, every kink in these rings is a breadcrumb leading us deeper into the dark. And as Hubble and its successors capture more of these cosmic contortions, we're not just mapping galaxies, we're decoding the invisible forces that shape them, one bend at a time. Deep within the fiery hoops of ring galaxies, the universe stages some of its most spectacular fireworks, displays supernova surges, where these cosmic explosions erupt in clusters so dense they outshine entire galaxies. Normally, supernovae are rare, isolated events, maybe one every few decades in a typical galaxy. But in these rings, they detonate like a chain reaction, with multiple stars exploding in quick succession, lighting up the void with bursts of energy visible across billions of light years. The secret lies in the ring's extreme star-forming conditions. When a galactic collision triggers that shockwave of compressed gas, it doesn't just birth ordinary stars, it forges stellar titans, massive stars dozens of times heavier than our sun. These giants live fast and die young, burning through their fuel in just a few million years before collapsing in catastrophic supernova. And because the ring's star-forming regions are so densely packed, These explosions ripple through the galaxy like dominoes, each blast triggering waves of new star formation and eventually more supernova. The Cartwheel Galaxy offers one of the most dramatic examples. Its outer ring is dotted with supernova remnants expanding bubbles of gas and radiation far more numerous than in any comparable spiral galaxy. Telescopes have caught multiple supernovae flaring up in the same region within years of each other, a phenomenon almost unheard of elsewhere, but the real shocker. These surges might not just be a side effect of the ring's formation, they could be fueling it. Every supernova blast injects the surrounding gas with heavy elements and shockwaves, squeezing it further and igniting yet another round of star birth. It's a self-perpetuating cycle where death begets life on a galactic scale. Yet the mystery deepens when we compare these rings to others with similar origins. Some, like Hoag's object, show almost no supernova activity despite having vibrant star-forming regions. Why the discrepancy? The answer might lie in the timing of the collision. If a galaxy's gas was mostly used up before impact, its ring might form fewer massive stars, leading to fewer supernova. Or perhaps magnetic fields, stronger in some galaxies than others, suppress the conditions needed for these stellar explosions. The implications stretch far beyond these glowing rings. Supernova surges could be the universe's ultimate recyclers, forging elements like gold, uranium, and oxygen, and blasting them into space where they'll eventually form planets and life. But they also pose a cosmic paradox. Could too many supernova doom a ring galaxy? Some models suggest these relentless explosions might blow away a galaxy's remaining gas, starving it of the material needed to form new stars and leaving it to fade into a ghostly red relic. Every detonation we observe is a clue, a snapshot of how violence and creation intertwine in shaping the cosmos. And as we watch these stellar fireworks flicker across the void, we're witnessing not just the death of stars, but the birth of galaxies anew. Some ring galaxies don't just expand gracefully, they hit an invisible wall. Imagine a ripple racing across a pond, only to freeze mid-motion, as if slamming into a sheet of glass. Astronomers have spotted rings that behave exactly like this, their outer edges abruptly stopping, as though some unseen force is holding them back. These aren't just cosmic curiosities, they're potential evidence of hidden structures in the universe, structures that could rewrite our understanding of how galaxies evolve. Take the case of NGC 1291, a ring galaxy whose outer edge looks like it was sliced clean with a knife. The ring's expansion should have continued for millions of years, its stars drifting outward like smoke in still air. Instead, it halted sharply, leaving a boundary so precise it defies conventional physics. The leading theory, magnetic fields woven through intergalactic space like an invisible net, might be trapping the ring in place. When charged particles in the galaxy's gas collide with these fields, they could be funneled into place, creating a barrier strong enough to counteract the outward momentum. But there's a wilder possibility: dark matter walls. Simulations suggest that during cosmic collisions, dark matter, normally diffuse, could clump into dense sheet-like structures. If a ring galaxy expands into one of these sheets, the dark matter's gravity might act like a brake, stopping the ring cold. Some astronomers even speculate that these walls could be relics from the universe's infancy, frozen remnants of the primordial chaos that birthed galaxies in the first place. The strangest part, not all rings hit these barriers. In galaxies like the Cartwheel, the outer edges fade gradually as expected. So why do some collide with invisible walls while others don't? The answer might lie in the angle of the original impact. A head-on collision could funnel dark matter into a flat plane, while a glancing blow might leave it scattered. Or perhaps the gas composition plays a role. Galaxies richer in ionized particles might interact more strongly with magnetic barriers. Then there's the ultimate question: what happens to the trapped material? Does it pile up at the edge, forming a glowing rim of compressed gas? or does it rebound, triggering secondary shockwaves that ripple back toward the galaxy's core? Observations from the James Webb Space Telescope hint at bizarre, glowing filaments at these boundaries, as if the universe itself is sketching an answer in light. Every halted ring is a puzzle waiting to be solved, a cosmic experiment revealing forces we can't yet see. And as we map these invisible walls, we're not just studying galaxies, we're uncovering the hidden scaffolding of the universe itself. Most galaxies are lucky to survive one cosmic collision, but some end up wearing their scars like tree rings, bearing the marks of multiple impacts stacked one inside another. Double-ring galaxies are the rarest of these survivors, their nested hoops resembling celestial bullseyes painted across the cosmos. At first glance, they look like impossibly perfect accidents, two shimmering circles of stars, one cradled neatly within the other, as if crafted by some divine draftsman. But peel back the layers, and you'll find a history written in violence, timing, and celestial precision. The secret to these dual rings lies in the rhythm of disaster. When one galaxy smashes through another, the shockwave triggers the first ring, sending stars and gas rippling outward like a stone dropped in a pond. But if millions of years later a second galaxy strikes at just the right angle and speed, another shockwave erupts, carving a second ring inside the first. The timing is everything. Too soon, and the second collision disrupts the original ring before it fully forms. Too late, and the galaxy's gravity might have already smoothed the first ring back into a disk. But when the strikes are perfectly spaced, the result is a galactic masterpiece, two luminous hoops, each a fossilized record of apocalypse. Take the stunning example of NGC 2623, a double-ring galaxy where the inner ring burns blue with newborn stars, while the outer one glows golden red with aging stellar populations. This color split isn't just beautiful, it's a timeline. The outer ring formed first, its stars given billions of years to cool and fade. The inner ring, birthed in a later collision, is still a stellar nursery, its gas not yet exhausted. The gap between these rings reveals the quiet eons separating the two catastrophes, like finding two cities buried in the same archaeological dig, one atop the other. Yet even among these cosmic twins, mysteries lurk. Some double rings, like ARP 147, show almost no gap in stellar age between their rings, as if both formed nearly simultaneously. How one radical theory suggests a single off-center collision might have sent shockwaves bouncing back and forth through the galaxy, triggering star formation in two distinct waves. Others argue these could be the aftermath of a trio of galaxies colliding in quick succession, a celestial pileup too chaotic for our models to yet replicate. The real enigma is how these delicate structures survive at all. Rings are inherently unstable, prone to fraying under their own gravity or neighboring galaxies' tugs. For two to persist requires a cosmic sweet spot, a galaxy massive enough to anchor them, yet isolated enough to avoid further disruptions. It's like balancing two spinning plates on a pole during an earthquake, a feat that should be impossible, and yet there they are. Every nested ring is a puzzle wrapped in starlight, forcing us to rethink how galaxies endure and even thrive in a universe that seems hell-bent on tearing them apart. The universe has a way of ironing out even its wildest creations, and ring galaxies are no exception. For all their striking beauty, these cosmic hoops aren't frozen in time. Gravity, the universe's ultimate sculptor, works tirelessly to unravel them, transforming fiery rings back into the familiar spirals we know. It's a metamorphosis that plays out over billions of years, a slow-motion dance where chaos yields to order and where the aftermath of a cataclysm becomes something entirely new. Computer simulations reveal just how delicate this process is. Start with a freshly formed ring galaxy, its stars still blazing in that perfect luminous circle. But gravity never rests. Over time, the densest clumps of stars within the ring begin tugging on their neighbors, creating tiny instabilities. these grow like cracks in ice, fragmenting the ring's smooth structure. Some regions pull ahead, others lag behind, and the once uniform hoop starts to warp. Slowly, almost imperceptibly, the ring develops kinks, seed points where spiral arms will eventually bloom. The Cartwheel Galaxy shows this in action. Hubble images capture faint, nascent spirals already forming along its outer ring, like tendrils reaching inward. Meanwhile, older rings like NGC 4680 display full-fledged arms emerging from their edges, as if the galaxy is reverting to its original form. But there's a catch. This isn't just a return to the status quo. The new spirals aren't identical to their pre-collision selves. They're laced with heavier elements forged in the ring's star, forming frenzy chemical fingerprints of the violence that birthed them. What's truly surprising is how quickly this can happen in cosmic terms. Simulations from the Illustris project suggest some rings begin unraveling in as little as 500 million years, a blink of an eye for a galaxy. The key factor, mass. Rings with lighter, more diffuse structures succumb faster to gravitational instabilities, their delicate balance easily disrupted. More massive rings, like Hoag's object, resist longer, their sheer bulk helping preserve their iconic shape against gravity's relentless pull. Yet even the stubbornest rings aren't immortal. Given enough time, interactions with nearby galaxies or internal turbulence will inevitably trigger their transformation. Some spiral arms might even inherit the ring's youthful vigor, continuing to birth stars at extraordinary rates long after the ring itself has faded. Others will settle into quieter lives, their once fiery hoops now just faint echoes in the starlight. This cosmic recycling raises a thrilling question. Could our own Milky Way have worn a ring in its distant past? Some astronomers speculate that the galaxy's thick central bar, a structure thought to form during collisions, might be the relic of such an event. If so, the spirals we see today could be the end stage of a metamorphosis billions of years in the making. Every ring galaxy we observe might not just be a spectacle, but a preview of our own celestial future. Some ring galaxies don't just glow with starlight, they pulse with invisible X-rays, their halos shimmering like ghostly coronas in the high-energy spectrum. These X-ray rings don't match the visible structure of the galaxy at all. Instead, they hover around the edges like cosmic afterimages, far larger and more diffuse than the starry hoops we see in optical light. What could possibly heat gas to millions of degrees, creating these ethereal halos? The answer might lie in the most violent events the universe can muster. Take the case of the Cartwheel Galaxy, where Chandra's X-ray vision revealed a faint but unmistakable glow enveloping its outer ring. Unlike the predictable X-rays from supermassive black holes or supernova remnants, this emission forms a smooth, continuous halo, almost as if the entire galaxy is bathed in an invisible furnace. The leading suspect, the accumulated fury of countless neutron star collisions. When these ultra-dense stellar corpses spiral into each other, they unleash bursts of energy so intense they can heat surrounding gas to X-ray temperatures. In a ring galaxy where stellar encounters are more frequent due to the dense packing of stars, these collisions might occur often enough to create a persistent glowing fog. Yet neutron stars can't explain every X-ray halo. Some, like the one around AM0644, show puzzling asymmetries, patches of intense emission on one side of the ring but not the other. Here, astronomers suspect something even more dramatic: shockwaves from the original collision, still reverberating through intergalactic space billions of years later. As these waves plow through sparse gas outside the galaxy, they could compress and heat it to X-ray temperatures, leaving behind a luminous but uneven imprint. The real mystery emerges when we compare these energetic halos to those of ordinary spiral galaxies. Milky Way-like galaxies typically have X-ray halos too, but theirs are faint and uniform, generated by steady processes like stellar winds or gently falling intergalactic gas. Ring galaxies, by contrast, scream their X-rays with unbridled intensity, as if the collision that birthed them left behind a lingering fever. This disparity suggests that the halos aren't just byproducts, they're thermometers, measuring the violence of a galaxy's past. But then there's the outlier, Hoag's object. Despite being a textbook ring galaxy, it shows almost no X-ray halo at all. Is it too old, its collision-shocked gas long since cooled? Or did it form in a way that avoided heating the surrounding medium? The silence of its halo is as revealing as the cries of others, forcing us to confront how much we still don't understand about these cosmic wrecks. Every flicker of X-ray light is a clue, a whisper from the most energetic processes in the universe. And as we piece together their origins, we're not just studying galaxies, we're reading the scars of their rebirths, written in a language of invisible fire. In the vast cosmic web where galaxies cluster like bustling cities, some ring galaxies defy expectations by floating in near-total isolation, glowing hoops adrift in the emptiness between superclusters. These solitary rings, like celestial hermits, present a paradox. If their signature shape requires a violent collision, how could they form where no neighboring galaxies exist to crash into them? The answer may rewrite our understanding of galactic evolution. Take UGC 4599, a perfect ring suspended in one of the universe's emptiest regions. With no large galaxies within millions of light-years, its pristine structure shouldn't exist under conventional models. Yet there it glows, its blue stars flickering against the void. Astronomers proposed three radical explanations. First, these rings might be survivors of galactic cannibalism, the last remnants of a dwarf galaxy devoured long ago, its stars stretched into a ring by a now-vanished predator. Second, they could be the ghosts of flyby encounters, where a fast-moving galaxy grazed another just enough to trigger ring formation before escaping into the void. The third possibility is the most unsettling. Some rings might form from the collapse of rogue, spinning gas clouds in the early universe, never part of a traditional galaxy at all. The evidence grows stranger when we examine these isolated rings up close. Many, like letter 1000704, show bizarre chemical signatures, abnormally high levels of heavy elements typically forged in dense galactic cores. This suggests they might be refugees ejected from galaxy clusters during ancient collisions, their rings forming as they were hurled into the void. Others, like NGC 7020, rotate too slowly for standard collision models, hinting at formation processes we've yet to imagine. The true enigma lies in their longevity. Without nearby galaxies to disrupt them, these rings could theoretically persist for tens of billions of years, far longer than clustered rings doomed by frequent interactions. Yet some show signs of instability, their shapes distorting as if tugged by invisible forces. Dark matter's gravitational whispers might be at work here, its uneven distribution in voids warping the rings over eons. Or perhaps the voids themselves aren't as empty as they appear, hiding diffuse gas clouds or primordial black holes that interact with the rings over cosmic timescales. These lone rings challenge the very definition of a galaxy. Are they truly isolated, or are we just blind to the dim, diffuse companions that might orbit them? Every new observation peels back another layer, revealing a universe where the rules of galactic life and solitude are far more flexible than we ever dreamed. Some ring galaxies hold ghosts of past violence, not just one, but multiple rings glowing faintly around them like celestial echoes. These secondary rings are cosmic time capsules, revealing collisions that occurred billions of years before the most recent smash-up that shaped the galaxy's current form. Picture tossing two pebbles into a pond at different times, the ripples spread outward, overlapping but never quite merging. In galaxies like NGC 2782, that's exactly what we see, a bright primary ring from a recent impact encircled by fainter, wider hoops of stars that mark the aftermath of ancient crashes. These echo rings are more than just relics, they are forensic evidence. By measuring their size and luminosity, astronomers can reconstruct a galaxy's violent timeline. The wider the secondary ring, the older the collision, its stars stretched thin by eons of orbiting the galactic center. In some cases, like the bizarre double-ringed galaxy AM0644, these echoes are so distinct they almost form a perfect target, with each ring corresponding to a separate impact separated by hundreds of millions of years. The staggering implication: some galaxies are serial crash victims, enduring multiple head-on collisions and somehow surviving each time. What makes these echoes so haunting is their impermanence. Unlike the primary rings, which shine with young, blue stars, the outer echoes are often dim and red, populated by aging stars that have drifted outward from the galactic core. Over time, gravity pulls these stars into ever wider orbits, thinning the ring until it dissolves into the void. That's why finding multiple intact echoes is so rare. It requires a perfect balance of timing, impact angle, and sheer luck to preserve them before they fade entirely. Yet the real mystery lies in the gaps. Some galaxies, like the Cartwheel, show only their youngest ring with no visible echoes, even though simulations suggest they should have endured at least 2 or 3 major collisions over their lifetime. Are the older echoes too faint to detect, or did something erase them? One provocative theory suggests black holes might be the culprits. A supermassive black hole's gravity could disrupt older rings, scattering their stars before they have a chance to fully form. Every faint echo is a whisper from the depths of cosmic time, a reminder that the universe never truly forgets its violence. It just lets the evidence drift ever outward, waiting for us to piece together the story. At the heart of every galaxy, hidden from plain sight, lies an invisible force shaping its destiny: magnetic fields. Normally, these fields follow elegant, organized patterns, spiraling gently along a galaxy's arms like cosmic fingerprints. But in ring galaxies, they're anything but orderly. Here, the fields twist into chaotic knots, looping in directions that defy logic, as if the universe itself forgot how magnetism works. The culprit: galactic collisions, the same violent encounters that forge these celestial hoops. When 2 galaxies slam together, the turbulence doesn't just rearrange stars and gas, it warps the very fabric of space's magnetic scaffolding. Imagine tossing 2 handfuls of iron filings into a whirlpool. The resulting mess, a tangle of lines crossing, snapping, and reconnecting, is what happens to a galaxy's magnetic field during impact. Telescopes like the Very Large Array have mapped these distortions in galaxies like the Cartwheel, revealing fields that don't align with the ring's rotation but instead spiral inward at odd angles, as if drunk on the aftermath of chaos. What's truly bizarre is how long these twisted fields persist. In most spirals, magnetic fields stabilize over time, smoothing into harmony with the galaxy's spin. But ring galaxies cling to their disorder. Some, like AM0644, show magnetic lines that loop backward against the ring's motion, creating pockets of resistance where gas struggles to flow normally. This could explain why some rings retain their fiery star-forming regions far longer than expected. The tangled fields act like cosmic brakes, slowing the dispersal of gas and keeping it trapped in the ring's grip. The real mystery lies in the extremes. In rare cases like NGC 4680, the magnetic field isn't just twisted, it's fractured, split into isolated domains that fight each other like rival factions. Gas moving through these regions heats unpredictably, sparking bizarre synchrotron radiation that glows in radio waves. Astronomers call this magnetic feedback, a phenomenon where the galaxy's own magnetism starts dictating its evolution, stifling star formation in some areas while supercharging it in others. Yet for all their chaos, these magnetic maelstroms might hold a key to galactic survival. Simulations suggest that twisted fields could stabilize rings against gravitational collapse, their tension acting like an invisible skeleton. Without them, these delicate structures might unravel far faster, their stars scattering into the void. Every kink in these magnetic lines is a clue, a reminder that even in the wreckage of cosmic violence, there's an invisible order waiting to be decoded. Among the most haunting spectacles in the cosmos are ring galaxies that should have died long ago, their star-forming gas exhausted, their brilliant blue stellar nurseries faded into memory. Yet these celestial zombies persist, glowing faintly with the golden light of ancient stars, their skeletal rings lingering like cosmic ghosts. Unlike their vibrant cousins, these undead galaxies haven't formed new stars in billions of years. So why haven't they disintegrated into the void? The answer might rewrite what we know about galactic life cycles. Take the case of Leda 10011714, a ring galaxy so ancient its stars date back nearly to the dawn of the universe. Its hoop of aging suns should have unraveled eons ago, pulled apart by gravitational tides or swallowed by neighboring galaxies. Instead, it hangs intact, its stars orbiting in eerie synchrony. The secret could lie in dark matter. An unusually dense, perfectly balanced halo might act like an invisible scaffold, holding the ring together long after its gas has dissipated. Simulations suggest these fossil halos could stabilize a galaxy indefinitely, like a fly trapped in amber. But not all zombie rings are so serene. Some, like NGC 2915, show bizarre patches of uneven brightness, their old stars clumped in irregular knots rather than evenly distributed. This suggests a turbulent past, perhaps sporadic encounters with intergalactic gas clouds that briefly reignited star formation before sputtering out again. These galaxies might not be truly dead but dormant, their embers still warm beneath the ashes. The debate rages: are we seeing the final flickers of a dying galaxy, or a hibernating giant waiting for its next cosmic meal? The most puzzling examples defy both explanations. UGC 4599, for instance, glows with stars nearly as old as the universe itself, yet its ring remains razor-sharp with no signs of fraying or distortion. Even more perplexing, its outskirts are littered with rogue star clusters, stellar strays that should have drifted away over billions of years. Could some unseen force, like a hidden black hole or a magnetic fossil field, be corralling these stars into place? Or are we witnessing a new class of galaxy altogether, one that evolves outside the known rules of astrophysics? Every flicker of light from these undead rings tells a story of resilience, defiance, and cosmic patience. And as we study their golden halos, we're not just observing galaxies in twilight, we're uncovering the universe's secret mechanisms for cheating death itself. Not all galactic rings blaze with the fiery glow of newborn stars. Some cling to existence as near-invisible ghosts, their sparse collections of stars stretching so thin they blur into the darkness between galaxies. These ultra-diffuse rings are the universe's failed experiments, haunting relics of collisions that lack the gas or force to ignite the brilliant rings we're used to seeing. Picture a cosmic donut spun from fog so faint that even the most powerful telescopes struggle to trace its outline against the void. What creates these spectral structures? The answer may lie in galactic collisions gone wrong. When two gas-poor galaxies collide, there's simply not enough raw material to fuel the explosive star formation that lights up classic rings. Instead of a luminous hoop, the impact leaves behind a skeletal framework, stars scattered so thinly they form more of a celestial cobweb than a true ring. The Antlia 2 ring galaxy is one of the most extreme examples. Its stars spread so far apart that if you stood on a planet inside it, the night sky would appear almost empty, your home star one of just a handful visible to the naked eye. Yet the mystery deepens when we study these faint rings up close. Some, like the recently discovered Phantom Ring in the Pegasus cluster, rotate at speeds that defy their sparse appearances. Their stars move as if bound by the gravity of a much denser structure, hinting at vast reservoirs of dark matter we can't see, silently anchoring these fragile star streams in place. Others show bizarre chemical signatures with higher concentrations of heavy elements than their low star density should allow. This suggests they might be the remnants of ancient, gas-rich rings whose stars have since drifted apart, leaving only the bones of what was once a vibrant structure. The most puzzling cases are those that appear to be forming now from ongoing collisions, yet still emerge to fuse. Computer simulations reveal a possible culprit: glancing blows. When galaxies collide at shallow angles or extremely high speeds, the resulting shockwaves may lack the force to compress gas efficiently, producing weak, scattered star formation instead of a concentrated ring. It's the difference between slamming two sheets of metal together to forge a gleaming blade versus lightly brushing them to produce only a dull shimmer. Perhaps the most haunting implication of these ghostly rings is what they tell us about galactic mortality. If ultra-diffuse rings outnumber their brighter counterparts, as some surveys suggest, then most galactic collisions might fizzle rather than ignite. The spectacular rings we treasure could be cosmic exceptions rather than the rule, their brilliance a rare gift of perfect timing, abundant gas, and precise impact angles. Every faint ring we discover whispers the same sobering truth. The universe prefers shadows to fireworks, and what we call normal might just be the outliers catching all the light. Among the rarest treasures in ring galaxies are time capsules, pristine star clusters that have somehow survived untouched since the galaxy's violent birth, orbiting like celestial museums frozen in time. These ancient stellar gatherings should have been torn apart eons ago by galactic tides or absorbed into the chaotic churn of the ring. Yet there they remain, glittering relics suspended in the cosmic amber of these hoops, their stars unmixed and undisturbed for billions of years. Take the Cartwheel Galaxy's outer ring, where Hubble spotted a cluster so old its stars predate the collision that formed the ring itself. Unlike typical globular clusters, dense balls of stars bound by gravity, these time capsules are looser, floating families that refuse to merge with the younger stars around them. Their survival defies expectation. The same shockwaves that compressed gas to forge the ring should have shattered or assimilated them. Instead, they drift serenely, their orbits perfectly balanced against the galaxy's gravitational pull. The secret may lie in their paths. Some clusters orbit just beyond the ring's densest regions, far enough to avoid disruptive tides but close enough to remain gravitationally tethered. Others, like those in NGC 7020, move in precise resonant orbits, each loop around the galaxy synced to avoid overlapping with the ring's most turbulent zones. It's a cosmic dance of precision, like a pendulum swinging eternally between chaos and order. But the real enigma is their composition. Many of these clusters harbor stars with unique chemical fingerprints, higher ratios of elements like lithium or europium than their neighboring stars. This suggests they formed in isolation, perhaps in the outskirts of the original galaxies before the collision, and were flung outward intact. Their purity makes them galactic archaeologists' dream, untouched snapshots of the universe's chemical state before the ring galaxy even existed. Why haven't neighboring stars polluted them? The answer might involve dark matter again. Simulations show that faint dark matter subhalos, invisible mini-structures nested within the galaxy's larger halo, could shield these clusters, their gravity acting like a protective bubble. Others propose magnetic fields fossilized in the cluster's gas might repel intruding stars, preserving their primordial state. Yet the most tantalizing clusters are those that shouldn't have survived at all. In AM 0644, a cluster orbits inside the ring's star-forming frenzy, surrounded by young, violent stars, yet remains chemically pristine. How? One radical theory suggests it's wrapped in a cloak of cold gas, its molecules so dense they act as armor against external forces. If true, these time capsules aren't just relics, they're fortresses, engineered by physics to outlast the chaos of the cosmos. Every undisturbed cluster is a message in a bottle from the distant past, waiting for us to decode its secrets. Some ring galaxies don't settle for a single, simple hoop. They weave themselves into cosmic lace, their structures so intricate they resemble celestial doilies stitched from starlight. These multi-ringed marvels aren't just visually stunning, they're galactic palimpsests, their overlapping circles recording multiple collisions or gravitational dances stretched across eons. Unlike the classic cartwheel-style rings born from single impacts, these layered structures suggest a far more complex history, one where galaxies don't just collide but collide again, each catastrophe leaving its own luminous fingerprint. Take the astonishing case of ARP 148, a galaxy so layered it looks like a bullseye carved by cosmic archers. Its innermost ring burns blue with newborn stars, evidence of a recent impact. But step outward and you'll find a second, fainter ring, older, redder, and slightly tilted, the ghost of a collision that occurred billions of years earlier. The most breathtaking detail, a third partial ring arcing across the galaxy's outskirts, as if some ancient galactic intruder merely grazed it before vanishing into the void. This isn't just a galaxy, it's a scrapbook of violence, each page written in starlight. The formation of these lace-like patterns hinges on celestial timing. When one collision's shockwave hasn't fully settled before another strike occurs, the overlapping ripples can create interference patterns, like dropping two stones in a pond at different times and watching their waves intersect. But there's a wilder possibility: orbital resonances. Some multi-ringed galaxies, like NGC 3081, show rings spaced at mathematically precise intervals, suggesting their structure stems not from fresh impacts but from the gravitational interplay between stars, gas, and dark matter. Picture a pendulum clock with multiple weights. Each component swings at its own rhythm, but occasionally their motions sync up, amplifying certain orbits while canceling others out. In galaxies, these resonances can funnel stars and gas into concentric circles without requiring new collisions at all. The true enigma lies in the exceptions, galaxies like UGC 5121, where rings crisscross at seemingly random angles, forming a celestial spiderweb. These chaotic patterns defy both collision and resonance models, hinting at forces we've yet to uncover. Some astronomers propose these could be splash rings, formed when a galaxy plows through a dense cluster, its outer stars torn away by the collective gravity of hundreds of passing neighbors. Others wonder if magnetic fields, twisted into knots during multiple mergers, might sculpt these irregular hoops like invisible hands molding cosmic clay. What makes these layered rings so precious is their rarity. Most galactic encounters either merge their participants completely or leave a single clean ring. Only under perfect conditions do these delicate, overlapping structures emerge and persist. They're the universe's way of showing off its most refined artistry, proving that even in chaos, there's a rhythm if only we know how to read it. Some rings in the cosmos don't glow with starlight, they lurk in the shadows, visible only when viewed through the infrared eyes of telescopes like Hubble and Webb. These phantom rings, ghostly structures of dust and cold gas, glow faintly with heat radiation while remaining utterly invisible in ordinary light. It's as if the universe has drawn these galactic hoops in invisible ink, revealing them only when we know where and how to look. The most famous example lies in the Andromeda Galaxy's neighbor, M32, where infrared scans uncovered a vast, dusty ring swirling just beyond its visible edges. Unlike the cartwheel's brilliant blue star factories, this ring emits no starlight, just the thermal whisper of dust grains heated by distant stars, the leading theory. These phantom rings are cosmic graveyards, the shattered remains of ancient collisions where gas and dust were flung outward but never compressed enough to ignite new stars. Over time, radiation pressure from the galaxy's core or passing supernova could have pushed this debris into a loose, glowing hoop, suspended like smoke around a candle. Yet the mystery deepens when we study their composition. Spectrographs reveal these dust clouds are laced with complex organic molecules, carbon chains, silicates, and even frozen water. Some astronomers speculate these could be galactic nurseries in waiting, reservoirs of raw material that might one day collapse into stars if disturbed by a passing galaxy or shockwave. Others argue the opposite. These rings might be galactic junkyards where stellar winds have dumped the ashes of dead stars over billions of years, their heavy elements glittering in the infrared like cosmic glitter. The real enigma is their structure. Unlike the sharp, star-filled rings we're used to, phantom rings are often frayed and asymmetrical, their tendrils stretching far beyond the galaxy's visible disk. In rare cases, like the one surrounding NGC 1291, the dust forms spiraling arms within the ring itself, a shape totally unexplained by current collision models. Could magnetic fields be sculpting these dust lanes into eerie patterns? Or are we seeing the gravitational imprint of dark matter, its invisible hands shaping the debris into these ghostly designs? Perhaps the most haunting possibility is that these rings aren't remnants at all, but thieves. Some simulations suggest they might be actively stealing gas from intergalactic space, siphoning stray atoms into their orbits over eons. If true, these phantom rings could be stealthy galactic predators, growing invisible reservoirs of fuel while the universe isn't watching, ready to ignite into brilliance when the time is right. Every infrared glow is a clue, a hidden chapter in the story of how galaxies grow, die, and hide their secrets in plain sight. Deep within the haunting emptiness of some ring galaxies, violent cosmic eruptions blast vast plumes of gas and radiation into space, structures so powerful they resemble celestial volcanoes. These aren't the tidy jets of active black holes or the symmetrical shells of supernova remnants, but chaotic fountains of matter erupting from the galaxy's core, spewing material at speeds that defy gravity. The Cartwheel Galaxy offers one of the most dramatic examples, where Chandra's X-ray vision revealed towering geysers of superheated gas punching through the central void, stretching thousands of light years into the surrounding darkness. What fuels these eruptions? The leading suspect is a supermassive black hole, not feasting steadily but choking on its own meal. When gas floods a black hole's vicinity too quickly, the infalling material can overheat, triggering violent outbursts of pressure that blast the surrounding gas outward. These aren't the focused jets we see in quasars, but wide-angle winds, hurricanes of particles and radiation that ram into the galaxy's remaining gas, carving out cavities and triggering shockwaves. In galaxies like AM0644, these winds might explain the eerie silence at the core. The black hole isn't dormant. It's clearing its throat with eruptions so powerful they've blown away the very material that could feed it. Yet black holes aren't the only culprits. Some rings, like NGC 3081, show volcanic plumes aligned not with the core but with chains of supernova remnants along the inner ring. When massive stars die in rapid succession, their explosions can overlap, creating a domino effect, each supernova's shockwave compressing neighboring gas until it too collapses and detonates. The cumulative force acts like a cosmic cannon, firing material outward in coordinated bursts. These supernova chimneys might explain the bizarre filaments seen in galaxies like Hoag's object, where tendrils of ionized gas stretch far beyond the ring's edge, as if the galaxy itself is exhaling stardust. The real mystery lies in the aftermath. Some of these eruptions leave behind glowing bubbles, vast structures of energized gas suspended in the galactic halo. Others, like the faint X-ray loops around the cartwheel, seem to vanish almost instantly, their material dissipating into the void before we can trace its fate. The difference might come down to magnetism. Galaxies with strong, organized magnetic fields could trap ejected gas in glowing halos, while those with fractured fields might let it escape like steam through a sieve. What's clear is that these eruptions aren't just destruction, they're transformation. By blasting heavy elements into intergalactic space, they seed future generations of stars and planets. And in the grandest irony, the same forces that tear these galaxies apart might be the very ones that knit the cosmos together. Some ring galaxies perform their own cosmic light show, vanishing acts where their glowing centers flicker and dim as if a celestial hand flipped a switch. These eclipses aren't caused by planets or moons, but by the galaxies themselves, their intricate dust lanes sliding into place like cosmic theater curtains. Picture a galactic bullseye where the central bullseye periodically fades, not because it's dying, but because it's playing hide and seek with its own structure. The mechanics of this shadow play are deceptively simple. In tilted ring galaxies like NGC 4680, thick bands of dust orbit in the same plane as the starry hoop. When these dust lanes align perfectly between Earth and the galaxy's core, they blot out the central light, sometimes for decades at a time. It's the interstellar equivalent of watching a street lamp dim as fog rolls in, except here, the fog is a churning cloud of cosmic soot stretching light years across. Hubble caught one such event in progress in the galaxy AM0644, where the core's luminosity dropped by nearly 40% over 12 years, its light smothered by a dust lane denser than the darkest nebulas in our own Milky Way. What makes these eclipses so extraordinary is their precision. Unlike random dust clouds that might drift erratically, these lanes follow strict orbital paths, their movements as predictable as clockwork. By tracking historical observations of galaxies like UGC 5121, astronomers have reconstructed eclipse cycles spanning centuries, some recurring as regularly as planetary transits in our solar system. The dust itself holds clues too. Spectroscopy reveals it's laced with frozen organic compounds, a murky cocktail of carbon and silicates that absorbs specific wavelengths of light, creating an eerie spectral fingerprint with each dimming. Yet the real mystery isn't the eclipses, it's why they're so rare. Most ring galaxies show chaotic, turbulent dust distributions, their particulate debris scattered by stellar winds or supernova. Only a handful exhibit these razor-sharp lanes capable of cleanly blocking their cores. The answer might lie in magnetic fields. In galaxies where magnetism aligns dust grains like iron filings, particles could self-organize into these precise bands. Or perhaps these rings are unusually calm, their lack of recent collisions allowing dust to settle into orderly orbits undisturbed. The most tantalizing cases defy all expectations. Take Hoag's object's distant cousin, LEDA 1000704, where the core doesn't just dim, it vanishes entirely for years, then reappears brighter than before. Some theorists suggest its dust lanes might be clumped into dense knots, acting like cosmic Venetian blinds that twist open and shut. Others propose the galaxy's central black hole could be belching intermittent plumes of soot, creating ad hoc eclipses when the mood strikes. These shadow dances aren't just celestial curiosities, they're time machines. By measuring how light filters through the dust, astronomers can reconstruct the chemical makeup of galaxies billions of years ago, long before Earth formed. Every dimming event is a fossilized whisper carrying secrets about how galaxies groom themselves, how dust evolves, and why some cosmic structures choose to hide their hearts in plain sight. Deep in the sparse outskirts of ring galaxies, where stars are few and gas drifts thin, the universe might be running physics experiments we can't yet comprehend. These low-density regions, cosmic deserts stretched between the bright hoops of starlight, are anything but empty. Instead, they could be playgrounds for quantum oddities, places where particles behave in ways that defy the rules we've written from our crowded corner of the cosmos. Take cosmic rays, high-energy particles rocketing through space at nearly light speed. In most galaxies, their paths are scrambled by magnetic fields and dense gas clouds, like pinballs bouncing through an obstacle course. But in the diffuse outskirts of ring galaxies, these particles might travel freakishly far without interruption, accelerating to energies beyond what our models predict. Some astronomers speculate these regions could act like natural particle colliders, where cosmic rays surf on shockwaves left over from the galaxy's violent formation, gaining energy over millions of light years. The result, rare, ultra-high-energy particles that shouldn't exist, and which might explain mysterious deep space signals we've detected, like the perplexing "oh my god" particle, a cosmic ray with the kinetic energy of a baseball packed into a single subatomic speck. Then there's dark matter's potential role. In most galaxies, this invisible substance forms a relatively smooth halo. But the collision that creates a ring galaxy could shred that halo into strange new configurations, filaments, knots, or even vast looping waves. If dark matter particles interact with each other even slightly, a big if in astrophysics, these distorted regions might be where we'd spot it. Imagine dark matter particles annihilating or decaying in these ghostly outskirts, producing faint bursts of gamma rays or neutrinos. Telescopes have already caught flickers of unexplained emission around galaxies like Hoag's object. Could this be the signature of dark matter finally revealing its secrets? The real wildcard, quantum vacuum fluctuations. In the near-perfect emptiness of these regions, where gravity's grip is weak and magnetic fields are sparse, the very fabric of space-time might behave differently. According to quantum theory, empty space isn't truly empty. It's a frothing sea of virtual particles popping in and out of existence. Normally, these fluctuations are too fleeting to detect. But in the extreme environment of a ring galaxy's outskirts, stretched thin by expansion and stirred by ancient shockwaves, some theories suggest these quantum bubbles might persist longer or grow larger, potentially leaving imprints on passing light or warping the paths of distant stars in ways general relativity can't explain. Every flicker of anomalous data from these galactic fringes is a tantalizing "what if" a hint that the universe's rulebook might have footnotes we've yet to read. And as telescopes grow sharper, these quiet corners of ring galaxies could become our best laboratories for discovering physics beyond our wildest theories. Among the rarest sights in the cosmos are ring galaxies that appear in near-perfect pairs, matching celestial twins spinning in distant corners of the universe like reflections in a cosmic mirror. These synchronized structures, almost identical in size, shape, and even star formation patterns, defy the odds. Galactic collisions should produce chaotic, one-of-a-kind wreckage, not matching sets. So when telescopes spot rings like ARP 247 and its doppelganger NGC 7020, separated by hundreds of millions of light years, both with sharply defined blue outer hoops and faint, redder inner rings, astronomers are left questioning everything. The leading theory suggests these mirror rings might be products of near-identical collisions occurring under freakishly similar conditions. Picture two spiral galaxies, each with matching gas content and rotational speeds, struck dead center by compact dwarf galaxies of comparable mass at precisely the same angle. The resulting shockwaves would propagate outward in eerily similar ways, compressing gas into star-forming rings of nearly identical proportions. It's like dropping two identical pebbles into separate ponds at the exact same velocity. The ripples would match even if the ponds were on opposite sides of the planet. Yet the statistical unlikelihood of this scenario is staggering. For two such collisions to produce rings so similar, the original galaxies would need matching masses, gas distributions, and even dark matter halos, a cosmic roll of the dice with odds akin to winning the lottery 10 times in a row. Some researchers propose an alternative. These twins might be fragments of a single gargantuan collision in the early universe, when two galaxy clusters slammed together, flinging matching ring galaxies in opposite directions like shrapnel from an explosion. Others wonder if dark matter's large-scale structure plays a role, its invisible filaments funneling galaxies into synchronized collisions across vast distances. The most unsettling possibility, these mirrors might hint at deeper symmetries in the universe patterns we've yet to recognize. Just as fractals repeat their shapes at different scales, could the fundamental processes shaping galaxies follow hidden rhythms? Certain simulations of cosmic inflation suggest the early universe might have contained regions with nearly identical initial conditions, leading to parallel structures forming billions of years later. If true, ring galaxy mirrors could be the first visible stitches in a grand tapestry of repetition woven into spacetime itself, but the skeptics have their own compelling arguments. What if these mirrors are just the survivors of a much larger, but now invisible family? Most ring galaxies unravel over time, their structures fading or distorting beyond recognition. The pairs we see today might be the only ones pristine enough to still resemble each other, their similarity a cruel trick of selection bias. Or perhaps their matching features are superficial, like two snowflakes that look identical from afar but reveal stark differences under a microscope. Detailed spectral analysis of these twins often uncovers subtle discrepancies in stellar age or chemical composition, suggesting their origins weren't as synchronized as they appear. The implications stretch far beyond these glowing hoops. If synchronized collisions are possible, they could revolutionize how we model galactic evolution, forcing us to consider the universe not as a chaotic free-for-all, but as a place where order emerges from violence in ways we're only beginning to glimpse. Every mirrored pair is a celestial riddle, one that challenges us to question whether the cosmos prefers chaos, harmony, or some intricate dance between the two. The universe is stretching itself apart, galaxies drifting away from each other as space itself expands. Yet amid this cosmic fray, some ring galaxies cling to their perfect shapes, refusing to unravel. These defiant hoops of starlight aren't just surviving, they're outright resisting the relentless pull of an expanding universe, as if sewn into the fabric of spacetime itself. What anchors them in place? The answer may lie in forces both familiar and utterly alien, weaving an invisible web that counters the cosmos' most fundamental rule. Take the enigmatic ring galaxy NGC 7020. Its outer edge so sharply defined it could have been drawn with a compass. While most galaxies stretch and distort over billions of years, this one's ring remains crisp, its stars orbiting at precisely the speed needed to counteract the universe's expansion. The secret might lurk in its dark matter halo, an invisible cocoon of mass so dense its gravity effectively glues the ring together. Simulations suggest that in rare cases, dark matter can clump into intricate, lace-like structures, creating gravitational anchor points that stabilize the visible stars against cosmic stretching. It's like a spiderweb strung across an ever-widening canyon, the silk threads taut, unyielding while the chasm grows beneath them. But dark matter isn't the only suspect. Some of these unyielding rings, like UGC 4599, show bizarre magnetic fields looping through their outer edges, fields strong enough to act as cosmic stitching. Charged particles spiraling along these magnetic lines could generate outward pressure, counterbalancing the inward tug of gravity and the outward pull of expansion. The result, a celestial tug-of-war frozen in equilibrium, where magnetic forces lock the ring's shape in place like a fly trapped in amber, the wild card in this cosmic balancing act. Quantum vacuum energy. In the emptiest regions of these galaxies, where matter is sparse and gravity weak, the vacuum of space itself might exert subtle repulsive forces. Theoretical models propose that if this energy varies in just the right way, concentrated along the ring's plane, it could create an anti-gravity effect, propping the structure up against expansion. It's a controversial idea, but if true, these galaxies might be the first visible evidence of quantum physics playing puppeteer on galactic scales. Yet the most tantalizing rings defy all three explanations. Hoag's object, for instance, lacks the dense dark matter or extreme magnetism predicted by these models, and yet its ring hasn't budged in 12 billion years. Could its stability be a relic of the early universe when expansion worked differently? Or is there some undiscovered law of physics, a hidden symmetry that favors circular perfection over chaos? Every unchanging ring is a challenge to our understanding, a glowing hoop whispering that the universe still keeps its deepest secrets close. Among the most mesmerizing structures in ring galaxies are those crisscrossed by radial streaks, spidery filaments of stars, and dust that stretch from the core to the outer edges like celestial spokes in a vast cosmic wheel. These aren't random fractures or imperfections. They're fossilized records of violence, remnants of the gravitational chaos that shaped these galactic hoops in the first place. Picture a stone tossed into a pond, not just creating ripples, but leaving behind faint, radiating lines where the water's surface was momentarily torn apart. That's the story these spokes tell, written in starlight and shadow. The Cartwheel Galaxy reveals one of the clearest examples, its outer ring sliced through by nearly a dozen faint, linear streaks. These aren't mere dust lanes, they're tidal tails, the stretched-out remains of smaller galaxies or gas clouds torn apart during the collision that birthed the ring. As the intruder plunged through the galactic disk, gravity pulled its stars into long, streamer-like filaments, which then became trapped in the expanding shockwave that formed the ring. Now, billions of years later, these ghostly trails orbit like threads woven into a spinning wheel, their presence betraying the violence of their origins. But tidal tails aren't the only explanation. Some spokes, like those in NGC 5296, trace their roots to an entirely different phenomenon, the corpse of a barred spiral galaxy. Before the collision, the original galaxy might have had a central bar, a dense, linear structure of stars common in spiral galaxies. When the impact occurred, the bar was shattered, but its debris didn't just vanish. Instead, it was flung outward, carried along the shockwave like driftwood on a tidal surge. Today, these scattered remnants form radial streaks, their alignment preserving the memory of the galaxy's pre-collision skeleton. The real enigma lies in the longevity of these structures. Tidal tails should dissolve over time, their stars dispersing into the broader ring. Yet in galaxies like AM 0644, the spokes remain razor-sharp, their stars moving in near-perfect synchrony. This defiance of cosmic erosion hints at unseen forces, perhaps dark matter filaments, knotted like submerged roots beneath the visible galaxy, anchoring the spokes in place. Or maybe magnetic fields twisted during the collision now act like cosmic guide wires, channeling stars and dust into these enduring formations. Then there's the rarest twist, spokes that glow brighter than the ring itself. In UGC 4599, radial streaks of young, blue stars blaze like neon signposts, their formation timeline utterly baffling. These stars shouldn't exist. They're too young to have formed during the original collision, yet too aligned to be random newcomers. The leading theory, the spokes themselves might be stellar nurseries, their dense gas and dust pockets shielded from turbulence long enough to birth new generations of stars. It's as if the galaxy, having shattered once, is now quietly knitting itself back together along these ancient fault lines. Every spoke is a clue, a breadcrumb leading us deeper into the labyrinth of galactic evolution. And as we trace their paths, we're not just mapping the aftermath of chaos, we're witnessing how the universe weaves order from wreckage, one radiant streak at a time. Deep in the silent expanse of space, certain ring galaxies pulse like cosmic heartbeats, their light flickering with eerie regularity, as if keeping time for the universe itself. These aren't random fluctuations, but precise, rhythmic brightness changes, some repeating every few years like clockwork. Take the case of NGC 2915, where the entire outer ring dims and brightens by nearly 15% on a 5-year cycle. At first, astronomers dismissed it as an observational glitch, but when the pattern held for decades, the hunt began for what could possibly orchestrate such a perfect celestial metronome. The prime suspect, a hidden dance of black holes. Imagine a supermassive black hole not anchored at the galaxy's core, but instead orbiting within the ring itself, trailing a cluster of stars and gas like a cosmic entourage. As this black hole plows through denser regions of the ring, It compresses surrounding gas, triggering temporary surges of star formation and X-ray emissions that brighten the entire structure. When it moves on, the glow fades until its next pass reignites the cycle. It's the astrophysical equivalent of a lighthouse beam sweeping across fog, its periodic flashes betraying the unseen giant beneath. Yet black holes aren't the only possible conductors. Some theorists point to resonant star clusters, groups of massive stars whose orbits sync up like pendulum swings in a grand clock. When these clusters converge at specific points in the ring, their combined gravity tugs on surrounding gas, sparking mini bursts of star formation that ripple outward as waves of light. In galaxies like AM0644, Hubble caught these clusters moving in near-perfect harmony, their synchronized orbits matching the ring's brightness peaks down to the month. The real mystery lies in the outliers galaxies where the pulses don't align with any visible structure. UGC 4599, for example, flickers every 11 years with no obvious black hole or star cluster to blame. Here, astronomers speculate about more exotic causes, perhaps dark matter clumps orbiting unseen, their gravity squeezing gas clouds at regular intervals. Or magnetic instabilities where twisted field lines snap and reconnect like cosmic rubber bands, releasing energy in predictable surges. Then there's the tantalizing possibility that these rhythms are echoes of the galaxy's birth. Simulations suggest the original collision might have set up standing waves in the ring's gas, vast, slow-moving ripples that take years to cross from one side to the other. As these waves crest, they could trigger star formation, creating brightness pulses that persist long after the collision's shockwaves have faded. It's like striking a bell and listening for centuries as the reverberations slowly dissolve into silence. Every rhythmic pulse is a cipher waiting to be decoded, a clue to forces hidden in plain sight. And as we tune our telescopes to these cosmic heartbeats, we're not just observing galaxies, we're learning to tell time by the universe's own wild, unyielding clock. At the hearts of most ring galaxies, you'd expect to find emptiness, scattered stars, perhaps a quiet black hole drifting in the dark. But a handful defy expectations, their cores blazing with the fiercest light in the universe, quasars. These cosmic beacons, powered by supermassive black holes feasting on gargantuan amounts of gas, shine brighter than entire galaxies. The puzzle: how do these sleeping giants awaken in the wreckage of a galactic collision? And why do only certain rings become their hosts? The answer might lie in the chaos of the collision itself. When two galaxies collide, especially if one is gas-rich, the violence doesn't just sculpt a ring of stars, it sends torrents of gas spiraling toward the central black hole. Picture a raging river suddenly redirected into a dormant volcano. The influx of fresh fuel ignites the black hole's accretion disk, heating it to millions of degrees until it erupts as a quasar, outshining every star in the galaxy combined. The Cartwheel Galaxy's neighbor, a ringed system called AM0644, showcases this in action. Hubble spotted tendrils of gas snaking toward its core, feeding a flickering quasar that pulses like a cosmic lighthouse. Yet the process isn't as straightforward as a simple gas delivery. Some quasars in rings flicker on hundreds of millions of years after the collision that formed the hoop, a delay that baffles astronomers. Simulations suggest the gas might take eons to spiral inward, like water slowly draining down a cosmic whirlpool. Other rings, like NGC 3081, show quasars that flare and dim unpredictably, as if the black hole is choking on its meal. These burping quasars hint at a delicate balance: too much gas at once, and the radiation pressure blows the incoming fuel away; too little, and the quasar fizzles out. The real enigma: some ring galaxies with identical collision histories don't birth quasars at all. Take Hoag's object, a near-perfect ring with a serene quasar-less core. The difference might come down to the black hole's original size. smaller black holes, even when flooded with gas, may lack the gravity to sustain a quasar's ferocious energy output. Alternatively, magnetic fields could play gatekeeper, their invisible lines funneling gas into stable orbits around the black hole instead of letting it plunge in. Then there's the wildcard scenario. What if the quasar itself reshapes the ring? The radiation blast from an awakened black hole is so powerful it can strip gas from the surrounding galaxy, halting star formation in the very ring that birthed it. In extreme cases, like the ring galaxy Roman 2 ZW96, the quasar's fury has blown bubbles in the surrounding gas, carving voids that stretch far beyond the galactic disk. It's a cosmic catch-22. The same process that ignites the quasar might also starve it, cutting off the gas supply that keeps it shining. Every quasar hosting ring is a time capsule, preserving the moment when a galactic wreck birthed a beacon bright enough to outshine time itself. And as we study their flickering light, we're glimpsing the universe's most violent rebirths, where disaster doesn't just forge beauty, but unleashes the hungriest monsters in the cosmos. Among the countless ring galaxies scattered across the cosmos, one stands out as a cosmic impossibility, a perfect, pristine hoop orbiting a galaxy so young it shouldn't even exist yet. Meet JWST-1, a celestial paradox glimpsed by the James Webb Space Telescope in what should have been the universe's turbulent infancy. This luminous ring floats around its host galaxy with mathematical precision, its blue stars blazing defiantly against the darkness. But here's what makes it unthinkable. Based on our current models, there hadn't been enough time since the Big Bang for two galaxies to collide and sculpt such an intricate structure. It's like finding a Renaissance painting in a prehistoric cave, a masterpiece where there should only be chaos. The numbers alone make JWST-1 incomprehensible. Standard galactic evolution theories suggest ring formations require at least 3 to 4 billion years, enough time for galaxies to mature, wander close enough to collide, and for the resulting shockwaves to settle into stable rings. But this one gleams in a galaxy just 800 million years after the universe's birth. Even if two proto-galaxies smashed together impossibly early, the resulting structure should be a messy, half-formed tangle, not this symmetrical marvel. Leading astrophysicists have run the simulations backward and forward, tweaking every variable: dark matter density, gas composition, collision angles, and the outcome remains the same. Under known physics, JWST-1 shouldn't be. Some researchers propose a radical solution: that our understanding of galactic formation is catastrophically incomplete. Perhaps the early universe birthed galaxies through processes we've never imagined, like direct collapse of spinning gas clouds into rings without collisions. Others wonder if dark matter behaved differently in the cosmos' youth, its peculiar gravitational effects enabling ultra-rapid ring formation. The most daring hypothesis suggests primordial black holes, tiny and countless, might have acted as cosmic sculptors, their collective gravity shaping gas into hoops long before traditional galaxies emerged. Then there's the fringe theory, the one that makes astronomers shift uncomfortably in their seats. Could JWST-1 be artificial? The idea isn't as outlandish as it sounds. A sufficiently advanced civilization harnessing energy on galactic scales might construct a megastructure to harvest starlight or manipulate spacetime. While most scientists dismiss this as sensationalism, the object's unnatural perfection keeps the debate alive. Its metallicity ratios, the precise mix of heavy elements in its stars, deviate subtly from natural expectations, as if someone tweaked the recipe. But perhaps the most unsettling truth is that JWST-1 might not be alone. Deep field surveys hint at other candidate rings in similarly young galaxies, their signatures faint but persistent. If confirmed, they could topple our cosmic timeline entirely, revealing a universe where beauty emerges not from slow evolution, but from laws we've yet to discover. Every photon from this impossible ring carries a silent challenge that the universe, even in its childhood, held secrets wilder than our boldest theories. From phantom rings that glow only in infrared to quasars flickering like cosmic lighthouses, from dark matter behaving in ways we can't explain to stars forming in eerily perfect synchrony, ring galaxies aren't just cosmic oddities. They're rule breakers, rewriting our understanding of how galaxies live, collide, and evolve. We've seen rings with no cores, rings that eat their neighbors, even rings spinning at impossible angles, each one a puzzle that defies the tidy explanations of astrophysics textbooks. These 30 phenomena prove one thing: the universe isn't just stranger than we imagine, it's stranger than we can imagine. Think about it. A single collision can sculpt a galaxy into a perfect hoop, ignite a frenzy of star birth, or awaken a sleeping black hole into a blazing quasar. Some rings vanish their own cores like cosmic magicians. Others pulse with rhythmic light, as if keeping time for the universe itself. And then there's JWST-1, that impossible ring in a newborn galaxy. Proof that the cosmos still holds mysteries we haven't even thought to question yet. What's clear is this: every ring galaxy is a laboratory testing the laws of physics in ways we'd never dare to recreate. So which mystery captivates you? Is it the way dark matter tangles itself into unseen knots, or how stars form in fiery, synchronized circles? Maybe it's those ghostly echo rings, faint whispers of ancient collisions still rippling through space. Or perhaps you've got a wild theory of your own about why some rings flicker like cosmic lighthouses while others simply refuse to fade. Drop your thoughts in the comments. Let's keep the conversation as boundless as the galaxies themselves. After all, the universe isn't done surprising us. Who knows what other rule-breaking wonders are waiting in the voids between the stars?